For more videos like this for Discrete 1, you can take a look at Sarai's studies. Link is in the description box below. In this video, we're going to talk about how to prove equivalences of compound propositions. So in simple words, if you have compound propositions, let's say compound proposition 1 and compound proposition 2, we want to know if they are equivalent. So this is the symbol for equivalence. And let's say that these compound propositions are made up of these propositional variables p and q, so both of these. And the whole idea is that for every possible truth assignment of p and q, no matter what p and q can be, the compound proposition 1 and compound proposition 2 should be the same, true and true. And if this is false, then this should be false. If this is true, then this should be true. And if this is false, then this should be false. In other words, they should be equivalent. They should be the same truth value for every possible truth assignment of p and q, no matter what p and q are. So in fancy words, what I just said, two compound propositions, compound proposition 1 that's made up of these propositional variables, however many number of them, and compound proposition 2 that's made up of these propositional variables are equivalent, and that's another way of writing it. Compound proposition 1 is equivalent to compound proposition 2 if and only if compound proposition 1 and compound proposition 2 have the same truth values for every possible truth assignment of the propositional variables. Another way to say this is compound proposition 1 is equivalent to compound proposition 2 if and only if compound proposition 1 implies compound proposition 2 and compound proposition 2 implies compound proposition 1 is a tautology. So in the last video, we discussed what a tautology is. All of the values of that compound proposition are true. In other words, we're looking for when this is true. If this is true, then you can say that these two compound propositions are equivalent because this is the definition of having the same truth values. This says if compound proposition 1 is true, then this should also be true. And if this is true, then this should also be true. And if that's the case for all of the possible truth assignments of p1 to p however number of propositional variables you have, then it's a tautology. Let's try an example. Prove that not p and q is equivalent to not p or not q. So we can do this two ways. We can prove equivalences using either method 1, which is truth tables, and method 2, known equivalences. What do I mean by known equivalences? Well, there's a cheat sheet that Garcia gives you. I don't know about any other professor in Discrete 1, but Garcia gives you exactly this on the exam. These are your known equivalences. These are just equivalences that other people have already figured out, and you're just going to use these known equivalences to prove that one compound proposition is equivalent to another. So we'll see how we do that. First of all, let's do the really easy way, which is using truth tables. So you disregard any operators. How many variables do you have? How many propositions do you have? Just two, p and q. So you want to do one column for each of your propositional variables. Then I noticed that we need a not p and a not q, so I'm going to do a column for these as well. And finally, I'll do one for the compound propositions themselves. And I can split this off into smaller pieces. So I can calculate this first, p and q, and then I can do not. I'm just going to label this as column 1 and just do not 1. And then I'll do this whole thing here. So instead of writing this, I could actually just do 2, 3. I could do 2 or 3. 2 or 3. Now let's zoom in here and try to do this. First question is, how many rows do we need? Recall that number of rows is equal to 2 to the n, where n is the number of propositions that you have. You only have 2 propositions. This is 2 squared, which is 4, so we're going to need 4 rows. Second question, how do we fill in the table? We take the number of rows divided by 2. We write it under the first column. Then we keep dividing by 2 until we get to 1. We're done. This tells me how many trues and falses I'm going to have to start off with. We want to start off with trues. So I'm going to do 1 true, 2 trues. I used up all my trues. I move on to my falses. 1 false, 2 falses. I used up all my falses, and I ran out of space in the column, so I move on to the next. So here I'm going to do 1 true. I used up all my trues. I move on to my falses. I used up all my falses. I still have space left. What do? I copy and paste the exact same pattern that I just have written until I run out of space. I run out of space, so I'm done. Not p is just a fancy way of saying opposite of p. So if p is true here, it's going to be false here. True here, false here, false here, true here, false here, true here. Not q, fancy way of saying opposite of q. So if q is true here, it's going to be false here, false here, true here, true here, false here, false here, true here. P and q, look at the operator. It's an and. In order for an and to ever give you true, this and this have to be true at the same time. So you're looking at p and q, these two columns, and you're looking for 2 trues. So here I see 2 trues, so it's going to be true. Here I don't see 2 trues, here I don't see 2 trues, here I don't see 2 trues, so it's going to be false. Here we have not 1. So we're just taking the opposite of 1. 1 is this column here. So if I see true here, opposite of that's false. False, true, false, true, false, true. And here I see 2 or 3. Remember, or operator. Only way or is going to give you true is if at least this or this is true. So you're just looking at these 2 columns, 2 and 3. So right here, and you're just looking for at least one of them to be true. Here, neither are true, so it's a false. Here I see 1 true, true. Here I see at least 1 true, whole thing is true. Here I see at least 1 true, whole thing is true. We're done with our truth table. Let's go back to what the question is asking us. They're asking us to prove that this, let's call this compound proposition 1, we can call compound proposition 1, is equivalent to, let's call this compound proposition 2. And what does our definition say? It says for every possible truth assignment of the propositional variables, in this case, what are propositional variables? Just P and Q. So for every possible truth assignment of P and Q, no matter what P and Q are, the two propositions have the same truth values. In other words, if this is false, this should be false. If this is true, this should be true. If this is true, this should be true. If this is true, this should be true. And they are. So because this compound proposition and this compound proposition have the same truth values for every possible truth assignment of P and Q, we can say that yes, these compound propositions are equivalent. So we use this definition, but I'm also going to show you how this is true by just calculating the double implication of both of these compound propositions in the truth table. So let me go ahead and make some space. So we want to calculate this over here. So we're doing the double implication of our first compound proposition and our second. If you recall, this is a double implication. Double implication only gives you true if you see twins. Think double twins. In other words, these here are twins. They're the same, so it's going to give you true. Here, these are twins. They're the same. It's going to give you true. Here, I see twins. They're the same. Going to give you true. Here, I see twins. They're the same. They're going to give you true. So what do you notice about this compound proposition? All of the values are true. What do we call a compound proposition where all of the truth values are true, no matter the truth assignment of P and Q? A tautology. T for true. So another way to see if two compound propositions are equivalent is just by finding the double implication of them. And if they're all true for every possible truth assignment of P and Q, in other words, it's a tautology, then these two compound propositions are equivalent. But notice something. In order to find the truth values of this compound proposition, you had to find the truth values of this one, which we did here, and of this one, which we did here. But notice how we got our answer without even doing this, because we could literally see that the truth values for these two compound propositions are the same for every possible truth assignment of P and Q. So it's kind of redundant. You don't actually ever need to do this. It's just a kind of a proof to show you that we can define two compound propositions being equivalent if the truth value for this compound proposition is a tautology. But you don't actually ever need to do it in a truth table. You could just end up here and be like, yeah, the truth values for both of these compound propositions are the same. Now let's do method 2, which is doing the same thing, proving that these two compound propositions are equivalent, but using known equivalences instead of a truth table. So let's go ahead and zoom in. The idea with using known equivalences, which is just a fancy way of saying all of these laws and identities, is by taking the longest side, this is the longest side in this case, or whatever looks more complicated, and trying to get it to look like the other side by using one of these identities or laws. So I'm going to go ahead and take this, not P and Q, and I'm going to say that's equivalent to what? Well, I'm going to look through here and I'm going to be like, what can I use? When you have a negation sign outside of two propositions connected with an and or an or, that's just a fancy way of saying, hey, distribute the negation sign to every single thing inside, including the sign or operator. So the opposite of P becomes not P. The opposite of this and becomes or. Opposite of Q, not Q. We call this De Morgan's law. You're literally just distributing the not to every single thing in here, which just means take the opposite of everything. That's what this one is. So every time you use a law, you have to write which one you use. And now notice we have exactly what we have on this side, so our goal is achieved. We got our long or complicated looking side to look like the other one. So we prove by using known equivalences, literally just the De Morgan's law, that this is equivalent to this, because that's exactly what we showed. This is equivalent to this. And just as a side note, you can always check your work using a truth table. So even on an exam, if they say use known equivalences, whatever you get at the end, you can always check if you're right by seeing if whatever you got at the end and whatever you started with in the beginning have the same truth values using a truth table. In this case, this is compound proposition 1, which is over here, and this is compound proposition 2, which is over here. And so if we want to check our work, we can see, yeah, they have the same truth values for every possible truth assignment of P and Q. So therefore, they are equivalent. And that's it for this video. In the next, we'll do a lot of practice proving equivalences using known equivalences, in other words, using this table.